Hello everyone, I am Berk and I will be presenting you our work Neural Radiance Fields Approach to Deep Multiview Photometric Stereo. Among the existing methods for 3D shape reconstruction, multiview stereo uses a set of images captured from different viewpoints. Although multiview stereo is very good at recovering the global geometry, it does not provide fine details of the surface. An alternative approach to recover surface details is using photometric stereo. Photometric stereo estimates the surface normals of an object from its light-varying images. It is excellent at recovering the fine details of the object, but cannot recover the global shape accurately. We know that the methods that rely on standalone approaches such as multiview stereo or photometric stereo suffer. As a result, multiview photometric stereo is generally employed. Multiview photometric stereo acquisition setup captures light-varying images from multiple views, so it can utilize the complementary behavior of multiview and photometric stereo in a single setup. However, existing methods for this task generally use simple and explicit mathematical models, which are unsuitable for surfaces with complicated BRDFs. Additionally, they use complex multistage fusion frameworks which are difficult to execute. In our work, we present a simple and general method that can suitably introduce the surface details coming from photometric stereo to neural radiance field representation of the scene. Now, let's have a closer look at the neural radiance fields approach, or simply NERF. NERF optimizes a volumetric representation of the scene as a function defined by any coordinate consisting of position and view direction. The function is parameterized by a fully connected network, which takes the 5D coordinates as input and outputs the volume density and RGB radiance at that location. Volume rendering techniques are then used to render any pixel along the camera ray. The fully connected network is differentiable and can be optimized by minimizing the error of the rendered pixel values. In our approach, we perform neural rendering of multiview images by blending the surface normal information with radiance fields representation. For that, we first estimate the surface normals for all the views using a deep photometric stereo network, which is trained independently in a supervised setting. Then we use the spatial location, surface normal, and viewing direction as input to our fully connected network. This approach introduces the information of the density gradient to the representation, encouraging improvements in multiview photometric stereo setup. To estimate surface normals from photometric stereo images, we utilize a deep learning framework. Choosing such a data-driven approach enables us to handle surfaces with complicated BRDFs without explicit mathematical modeling. We also use an observation map strategy, which is shown to be very effective in estimating per pixel surface normals. For that, we construct observation maps for each pixel using observed intensity values due to all the light sources. Then we learn a mapping between the observation maps and the corresponding ground truth normals by minimizing the L2 loss function. After the deep photometric stereo network training is complete, we predict the surface normals of an object. Then we use the predicted surface normals as input to our fully connected network along with the sampled position and viewing direction. Similar to NERF, we use Fourier feature encodings of the inputs to learn high-frequency variations in color and geometry. We also adapt coarse-to-fine volume sampling approach for efficient evaluation during volume rendering. We optimize network parameters such that the rendering loss for both coarse and fine sampled rays are minimized. We evaluate the performance of our method on diligent multiview dataset. Here we compare the 3D reconstruction accuracy using chamfer L1 metric. The statistics show that our method is better than the standalone methods and comparable to the multistage fusion methods. In addition to that, our method is more favorable than the complex multistage fusion approaches because it is simple to execute and realize. Now, let's have a closer look at the rendered images. Here we show that our method provides much higher image rendering quality compared to the standard NERF. It indicates that surface normal information is crucial for learning high-quality scene representations, and that's why our method can render images with fine details. To sum up, we propose an opportunistic approach to solve multiview photometric stereo problem by exploiting the surface normals in volume rendering. We show that we can learn better scene representations as the surface normals provide information of the gradient in the density space. As a result, our method demonstrates improvements in 3D reconstruction accuracy and image rendering quality. Thank you.